If you look at the look up the ionization energy of sodium, you'll find that it's 5.1 electron volts. In other words, if I were to remove an electron from sodium, that's going to require an input of 5.1 electron volts. On the other hand, if you look up the electron affinity of fluorine, if you attach an electron to fluorine, you're going to get fluoride ion, and the electron affinity is 3.4 volts. So it's going to release 3.4 volts. So the difference between these two is 1.7 electron volts. It takes more energy to remove an electron from a sodium atom than the amount of energy you can release by putting that electron into a fluorine atom. So that's not exactly what we would consider a favorable condition for forming noble gas-like ions. Remember, sodium is a noble gas-like, has a noble gas-like configuration. Fluoride has a noble gas-like configuration. It does actually require energy of 1.7 electron volts. Where does the stability actually come from? It is achieved when the cation and the anion move closer together. If you remember, you can plot potential energy versus the distance between two particles. So in the case of two ions, typical plot would still look like this. Okay, so this is potential energy versus distance. Distance here is r. Okay, and in fact, if this well depth, we talked about this earlier in the semester, is about 5.3 electron volts. Okay, so when your sodium, oops, this should be fluoride, and fluoride. If your sodium and your fluoride ions in the gas phase were to get together, okay, this well depth is 5.3 electron volts. A third body has to come in, okay, and take away 5.3 electron volts. So this is your bond dissociation energy. If you have a sodium fluoride, this should be sodium fluoride, I'm sorry about that. If you have a sodium fluoride molecule in the gas phase, okay, if a pair of sodium and fluoride ions stuck together in the gas phase, not in the solid, in the gas phase, for them to be able to separate, somebody has to come in and give them 5.3 electron volts. Similarly, for these two ions in the gas phase to get stuck, somebody has to take away at least 5.3 electron volts for them to get stuck. Okay, so that's your, and they're not going to get stuck if the third body doesn't come in, because eventually they're going to get so close together, and the charged particles are going to be so crowded, there will be a net repulsion. Okay, and so they'll still separate if the third body doesn't participate in the process. Okay, now, so that's 5 electron volts released by just giving release to a third body when those two ions get together to form a molecule in the gas phase. Okay, like I said, this is fluoride. Okay, and once, in fact, and then from the gas phase, if you go all the way to form solids, if you have these ions get together to form a solid, then it will release even more energy. Okay, as you know, ionic compounds, as they exist in nature, are, under ordinary conditions, are solids. Okay, that will involve an even bigger release of energy. The total energy release in going from ions in the gas phase, sodium and fluoride ions in the gas phase, to sodium fluoride in the solid, okay, would be 9 electron volts for every pair, on average 9.5 electron volts for every pair of ions. This is what's called the lattice energy of the solid. So that involves a tremendous amount of energy release and a lot of stabilization going on there.